I'd like to take you through a strategy for differentiation called implicit differentiation. And to get us started, I asked you to do this as a warm-up question. We have a circle here. It has the equation x squared plus y squared equals 4. And what I would like you to do is I would like you to find the slope of this tangent line that goes to the point positive 1, negative root 3. So if you haven't done that already, take a second, try this question, see if you can find the slope of this tangent line, and then we'll go through a solution together. Okay, so here is one solution for this problem. So you'll notice this is a little bit different than many of the other derivatives that we've calculated over the course of the last little while because it has an x squared and a y squared in it. So instead of being written as y equals something with respect to x, it's got the x squared and the y squared here in this relationship. So the first thing that you can do is you can take this relationship and rearrange it to isolate for y. So I start off with x squared plus y squared equals 4. I'm going to subtract x squared from both sides. So I get y squared equals 4 minus x squared. And then I want to isolate for the y, so I take the square root of it. And we know that when we square root something, we've got to consider both the positive and the negative square root to get our to isolate for the y. So in this case, I get plus or minus root 4 minus x squared. And that connects nicely up here with our circles. So the positive root 4 minus x squared is going to be this pink part here, the top part of the circle. And the negative root 4 minus x squared is going to be the bottom part of this circle. So in this case here, if we want to find this tangent line slope through this point down here, we're going to want to use this part of the function, this function that represents this part of this whole relationship, which is y equals negative square root 4 minus x squared. So we're going to focus in on that. And I'm going to find the derivative of this, sub in my point, and that will allow me to see what the slope would be at that of the tangent at that point. So I like to rewrite, when I have a square root, I like to rewrite it as an exponent. So I just rewrote this function as negative bracket 4 minus x squared to the power of 1/2. That allows me to easily take the derivative using the chain rule. So I'm going to bring down that 1/2. So I get negative 1/2, 4 minus x squared to the power of negative 1/2. And then I'm going to take the derivative of the inside, which is negative 2x. So I simplify that. I'm going to bring this down because it's now a negative exponent. My negative 2x stays on top and combines with this negative 1. So I get positive 2x on the top. My 2 stays on the bottom. This shifts down, so I get the square root of 4 minus x squared on the bottom. And in simplified form, I end up getting y prime equals x over the square root of 4 minus x squared. So now that I have my derivative function, I can sub in my point 1 negative root 3 into my derivative, and I end up getting 1 over root 3, and I just rationalize the denominator here to get root 3 over 3. So if I look back now at my picture, that means that the slope of this tangent line that goes through the point 1 negative root 3 is about root 3 over 3. So positive makes sense, and we're good to go. So what I want to show you today now is another way to handle finding the derivative of a relationship like this when we have both x's and y's involved. Up until now, most of the things that we have been doing have been expressed explicitly in terms of y. So we're going to use two things. First of all, we're going to be using what's called the chain rule. So remembering the chain rule back when we were learning our derivative rules, that if we have a function and an inside function, then we always just tag on the derivative of the inside function after we've taken the derivative of the original function. And then also the word implicit. So the word implicit means implied though not plainly expressed, where explicit means that things are pretty clear, it's explicit. And like I said, up until now, most of the derivatives that we have calculated have been functions that have been explicitly been written as functions in terms of x. So for example, here I have y is equal to x squared plus 4. So x, this function is written explicitly in terms of y and x. It is clear what the y is, it's clear what the x is. And I can then easily calculate the derivative. Y prime is equal to 2x. So this is what we've been doing so far. What we want to do is now is we want to take this and we want to start looking at how we can work with functions that are not so explicit, hence the word implicit differentiation. So the question that we just worked on, let's try doing this another way. So let's try to do it without explicitly writing or writing y explicitly as a function of x. So instead of doing that initial step of rearranging it and isolating for y, let's just work with the way the relationship is already written. So what I'm going to do is I'm going to have x squared plus y squared equals 4. And what I'm going to do is I'm going to take the derivative of both sides. So I'm applying a function of calculating the derivative to both sides. So I'm going to find the derivative of x squared plus y squared and the derivative of 4. Now, when I have the derivative of this side here, I know that I can take the derivative of each piece of this side. So I'm just going to rewrite this. And again, you don't have to do this step, but I just want to make it clear what I'm doing. So I'm going to take the derivative of x squared, I'm going to add that to the derivative of y squared, and I'm going to, again, have that equal to the derivative of 4. So now I'm actually going to calculate my derivatives. Well, I know that the derivative of x squared is just 2x. So the derivative, or d by dx of x squared is just going to be 2x. So that one's pretty straightforward. However, what do I get when I take the derivative of y squared? Well, this is where that chain rule is going to apply. So what I'm going to do is I'm going to take the derivative of y squared as it is. So that becomes 2y. And then it's almost like I have an inside function of y. And the derivative of y is y prime. So I'm going to rewrite this using the chain rule as 2y times y prime. I'm going to keep going because I know that the derivative of 4 is 0. So now I have this new expression that says 2x plus 2y times y prime, because I applied the chain rule there, is equal to 0. So I broke it into pieces and I took the derivative of each piece. So now I have an expression that has y prime in it. And remember, that's what I'm trying to find. So what I can do is I can rearrange this expression or this equation and isolate for y prime. So I'm going to take this, so I'm going to subtract 2x from both sides. So I'm going to have 2y, y prime equals negative 2y. And now I want to get the y prime by itself. So divide both sides by 2y, divide by 2y. And then I can actually isolate this. Sorry, I didn't do it here, but I could cancel it, the 2's. I get y prime is equal to negative 2x over 2y, or negative x over y. So if I had to simplify that, I could have taken that a little bit further. So now if I want to calculate that slope of the tangent at the point 1 negative root 3, then all I have to do is just plug in my x and my y of my point into my derivative function. So when I plug that in, I end up getting 1 over root 3, or 3 over root 3, which is what I found when I did it the other way. Okay. The beauty of doing it this way, though, is that if I also wanted to find the derivative of other points, like so if I wanted to find the derivative of the point 1 positive root 3, it's already written nicely for me. I don't have to go back and use that top function. I can just use this derivative function that I found implicitly, and I could sub in my point 1 negative root 3 because it takes into consideration both the x and the y when I'm calculating my derivative. So it's a nice, efficient way of being able to come up with a function that we can use to find the derivatives of a whole bunch of different points when we're dealing with relations rather than just functions here. Okay, so we take the derivative of both sides, we break it into pieces and take the derivative of each piece, we rearrange it to solve for y, and then we plug in the point to find the value, the instantaneous rate of change at the point that we're trying to, that we're working with. Okay, so let's try this out for a different example. Like I said, this is called implicit differentiation because it's a technique that we use to find a derivative when y is not explicitly defined in terms of x, but it is still differentiable. So that's a key thing. It has to be differentiable, but it doesn't require us to do that initial step of isolating for y, because in some functions too, that can be really difficult to do. So actually, this would be a function right here that would be really difficult to do that with. Here we have the function x sine y equals cos of x plus y. So if I asked you to take this and isolate for y, that would be a very difficult task because we've got these y's locked in here to the angles, and then being able to trying to rearrange that to get y by itself, that would be a chore for sure. So let's use the method of implicit differentiation to see if we can find y prime, using that new strategy. And just so that you can see this is a neat picture. I plugged it into Desmos, and this is a picture of what this function looks like. So you can see that it would be a challenge for sure. And okay, let's go. So here I'm going to start off. I'll zoom in a little bit here. So I'm going to start off by taking the derivative of the left side and the derivative of the right side. So find the derivative of x sine y and the derivative of cos y, x plus y. So over here, this derivative is going to be a little bit more challenging because I'm actually going to have the product rule incorporated in here. So here I have x times sine y. So remember, the product rule says that I'm going to take the derivative of my x and times it by sine y, and then I'm going to take the derivative of sine y and times it by my x. So the derivative of x is 1. I'm going to times that by sine y. And then my derivative of sine y is going to be cos y, but then I'm going to take the derivative of that y and tag it on here because I've got to take that derivative of the inside function. And I know that the derivative of y is y prime. And I'm going to times that by my first function, which is x. So on the left side, I end up with sine y plus x cos y times the derivative of y, or y prime. On the second side, I don't have a product this time, but I am going to have to apply that chain rule again because I've got a function within a function. So I'm going to start off by taking the derivative of cos of x plus y. So the derivative of cos is negative sine x plus y. And now I'm going to take the derivative of my inside function. So the derivative of x is just 1, and the derivative of y is y prime. So when I take this and I expand it out, I'm kind of going backwards here. I'm going to take negative sine x plus y and times it by 1. And I'm going to take negative sine x plus y and times it by y prime. So on the right side of my equation, I end up with negative sine x plus y, which is my times 1, and minus, I'm going to put my y prime in front. So I've got y prime sine of x plus y. Okay, so we've got a pretty complicated looking relationship here that we've created. But now we want to go through and see if we can find a way to isolate for our y primes, or our derivatives of y. So I'm looking over here, and this has a y prime in it, so I'm going to keep this on the left side. This one doesn't have a y prime in it, so I'm going to move it over to the right. I'm going to keep this on the right because it doesn't have a y prime in it, but this one does have a y prime in it, so I want it over with the y prime on the left, so I'm going to take this and I'm going to add it to both sides to bring the y prime over to this side. So I've got all of my terms with the y prime on the left side and all of my terms that don't have y prime on it on the right side. My next step here is to get this y prime by itself. And you'll notice that because I grouped them all over onto the left side, I can factor out a y prime. So I factored out a y prime from both sides here. And when I take y prime and factor it out of this expression here, I end up with x cos y. And when I factor it out of this here, I end up with sine of x plus y. So I'm going to have this left over once I factor out my y prime. And to get my y prime by itself, I simply have to divide both sides by this expression. So if I divide this side by that expression and this side by that expression, I end up with y prime is equal to negative sine x plus y minus sine y over x cos y plus sine of x plus y. And now you can imagine, now I know that a function for, a relationship that I can use to help me find the instantaneous rate of change at any point on this function. So I can choose any coordinates x, y, any point, plug them into this derivative relationship, and the instantaneous rate of change at that point will come out. Okay, so it looks really complicated, but we've actually made things a lot easier for ourselves because now all we have to do is plug in our point to find our instantaneous rate of change. Okay. Okay, one more example to work through. This time, I want you to find two things for me. I want you to find dy by dx, so the derivative of y with respect to x, and I want you to find the second derivative of y with respect to x. And I, again, have a circle here, so I have an x squared plus y squared equals 1. So we could always take this, rearrange it, isolate for y, and then do the two pieces independently, find each one of those derivatives, and then do it again. But I want you to try to do it implicitly. So I want you to see if you can use implicit differentiation 2 times to come up with both the first derivative and the second derivative. So I would like you to pause the video, take a minute, try the question, and then come back and see a solution. Okay, so here is my solution. So I have my relationship here. I'm visualizing a circle, and I'm going to take the derivative of the right side and the derivative of the left side. So I end up with the derivative of x squared plus the derivative of y squared equals 0. Well, I know the derivative of x squared is 2x. The derivative of y squared is 2y times y prime equal to 0. And I'm going to isolate for y prime, and I end up with negative 2x over 2y, which reduces down to y prime equal to negative x over y. So again, instead of having to do two different functions, I now have a function that uses both parts of the point, the x and the y, to calculate the instantaneous rate of change at that point. Okay. If I wanted to know concavity at that point, it would be really helpful for me to know the second derivative. So I know that quotient rule tells me that I take the derivative of my top and times it by my bottom, and then I subtract that from the derivative of my bottom times my top, and then I'm going to take my bottom or denominator and I'm going to square it. So derivative of negative x is negative 1 times that by my bottom, which is y, minus the derivative of my bottom, y. Well, the derivative of y is y prime, times that by my top, which is negative x. And then I'm going to square my bottom, which is y squared. And I could do a couple different things. So if I had a particular point that I was working with, I could take that point and I could plug it back into here, figure out the value of the derivative at that point, and I could plug it right into here, into my y prime. Or I can take my function that I came up with for y prime and sub it in for y prime and then simplify it. So that's what I chose to do here, just so that I could use the second derivative for a whole bunch of different points. So I took y prime, which I know is negative x over y, and I subbed it in for my y prime. And after I simplified it, I ended up with negative y over x squared over y all over y squared. So again, if I know the coordinates of any point on my relationship x, y, all I have to do now is sub them in. That allows me to calculate the second derivative, and from there I can tell about what is going on with the concavity of that relationship at that particular point. So hopefully this gives you an idea of how to implicitly differentiate relationships that are a little bit more complicated and have both x's and y's in them. And there you go.